гости! Имам честта да обявя решение на Академичния съвет на Софийския университет за удостояване на професор Клаас Бергман с почетното звание доктор хонорис кауза на Софийския университет Свети Климент Охридски. Предложението за удостояване с почетното звание на най-старото висше училище в България е на физически факултет и е инициирано от катедра теоретична физика. Професор Клаас Бергман е роден през 1942 година в Германия, учи физика в Фрайбург, където през 1972 година защитава докторат, след което е постдокторант в Беркли. Кариерата му преминава основно в Техническия университет на Кайзерслаутен, където е назначен за асистент през 1975 година, а от 1981 година е професор. Пенсионира се през 2007 година, но остава ангажиран с научна дейност. Назначен е за старши научно-изследователски професор в Техническия университет на Кайзерслаутен за периода 2007-2015 година, което е прецедент в провинция Райнфалд-Пфалц. От 2017 година е нает като научен ръководител на проект за разработка на нов тип лазери от топите. Професор Бергман координира множество национални и международни научни проекти, служи като заместник-председател и председател на панела по физика в мрежата за иновативно обучение на програмата Мария Кюри на Европейския съюз в периода 2008-2017 година. Член е на множество професионални организации, като Американското физично дружество, Германското физично дружество, Американското оптично дружество и Европейското физично дружество. Професор Бергман е автор на около 200 научни публикации с повече от 10 500 цитирания. Хаш индекса му е 50. Една от публикациите му има над 1600 цитирания. Характерна особеност на неговата научна работа е разработването на лазерно базирани методи, позволяващи нови експерименти в квантовата динамика и квантовата оптика. Професор Бергман е носител на редица научни награди, награда за изследовател на Годеке, награда за физика, награда Робърт Уичард Пол, награда Макс Планк Ресърч, почетна докторска степен на Латвийския университет в Рига, орден за заслуги на провинция Райнфалд-Пфалц от 2005 година, награда на Nature за природно-научна дейност за 2008 година. През 2020 година е удостоен с наградата Дейвисън Гемер на Американското физично дружество. Тази награда се счита за едно от най-високите отличия в областта на атомната, молекулната и оптична физика. Предишни лауреати от атомна физика на тази награда включват 5 Нобелови лауреати. Лазерно-индуцираният процес, широко известен като стрипак, разработен от професор Бергман и неговия екип, не за първи път получава международно признание дори след 25 години. Това е незаменим инструмент за детерминистичен контрол на атомна кохерентност в квантовите технологии. Професор Бергман е активен поддръжник на интегрирането на страните от бившия съветски блок в европейското научно пространство. Има значително по обем и качество сътрудничество с учени от Физическия факултет на Софийския университет и Института по физика на твърдо тяло към БАН, с повече от 30 съвместни публикации и 3 съвместни големи европейски проекта. Бил е домакин на 6 докторанти и постдокторанти от Софийския университет и БАН. Посещавал е Софийския университет 8 пъти и е изнесъл 3 доклада. Позволете ми в този момент да поканя заместник-ректора професор Витанов и лауреата за връчване на награда. Заповядайте. Професор Витанов.
Висше училище в Срядци, наречено е именем Присноблаженного учителя българского Климента Охридского. Повядава да се художество, физического учения, еже съвършилост еста. Професора Клаас Бергман, технослованного висшего училища в Кайзерслаутерния гряде. Съчастион глашаята его басано почетного доктора висшего училища Климента Охридского. В Срядци мясенца мая 97 валято 700 и 500 и 30 от сътворения миро. Universitas Literarum Servicensis. Nomine Sancti Clementis Achridensis ex sententia facultatis scientiarum physicarum. Virum eminentissimum atque referendissimum Professorem Doktorem Клаас Бергман, Doktorem honoris causa, Scientiarum Physicarum Universitatis Cervicensis, nominavit atque declaravit, in eiusque rei fidem hoc diploma sigillo maiore universitatis roburatum et consuetis, subscriptionibus munitum eidandum curavit. Datum service ante diem sextum calendas iunas anno domini bis millesimo vicesimo secundo, rector universitatis. Сега думата за академично слово има професор Бергман.
This methodology is something which we developed, and none of whom made substantial contributions to it. It's a method for robust population transfer between quantum states. It's actually the best-selling scientific product from my group, and it's now used worldwide. And here, oh, okay, yeah, it's fine, okay. Here now, how it came about. Let's look at the situation before 1990. Before 1990, we had this Iron Curtain in Europe. All of you, at least, except for the very young ones, they know about it. But even during that time, I had some contact to Eastern Europe. The first one was to Bucharest, then then came Budapest and Riga. And Zagreb from Croatia, and Prague from Czechia now, and Poland, Warsaw, and Togo. So I had quite some contact to colleagues from Eastern Europe, both coming to my lab, as well as seeing them, most of them, in their own lab. So from that experience, from these visits, I experienced, and I knew what I have read, what I experienced myself, that there is excellent science education done in these places, and also excellent research in these countries. So, okay, this is one element. And the other element is an observation which I made during the 2 years after the Iron Curtain fell, that there was a scientific brain drain from the East to the West. So many people, in particular the young, promising ones, tried to go to the Western communities, United States, to make a career there. And I consider this problematic not only for Eastern Europe, but also for the West, because science is education and it's exchange, and you need strong partners for doing science. So in 1992, I actually made a conscious decision, and I communicated this to my group during one of these typically informal after lunch meetings, and actually surprised my group with this statement. I said, I want to seek new contacts to Eastern Europe, active contacts, even at the expense of Western contacts, in particular the United States. So I did not expand in this direction, but I wanted to have new contacts to Eastern Europe. And I wanted to encourage, this was also part of the decision, to encourage the visitors to return to their home country in order to help establishing some strong science groups, and with using some of the experience which they have made in the West. When I told this to my students, they didn't really understand what I was talking about, but they soon realized that this was a good decision. Since, as I mentioned, my experience prior to 1990 was that there is good science, so I did not do this only to help these colleagues from the Eastern Europe, but also for myself. So I really expected a win-win situation, both for the visitors and in particular for myself, and this really turned out to be really true. So the first step after 1990, right after 1990, was to reactivate my contacts to Riga, which lasted already more than 20 years. And even I visited Riga earlier, and then the next step was to be ready for new contacts. I didn't know how they would come about, but I was simply ready to make use of opportunities. And I will describe 3 things with little stories. So the paper 1 story is the contact to Yerevan. And this story goes like this. Our first paper about stirrup, which I will briefly mention at the end what it is, was in 1988. And in this little short paper, we showed that this concept works, population transfer, in a very specific way. But we hadn't understood it yet fully, and so the theory was incomplete. And a colleague from Yerevan, Armenia, read this paper, and he said, well, I will sit down and I will do the complete theory. But this takes some time. And then, before submitting the paper, we had published our famous 1990 paper. I can't call it now famous because it's the original Europe publication with lots of new data and the complete theory in its very simplest form. And and this is what the colleague Boris Lushko from Armenia realized, and therefore he did not submit his paper. So he went then to a conference in Amsterdam, met a student of mine there, and he told him this story. And the student told me. So I immediately invited Boris Lushko to Kaiserslautern. He came for a couple of days, and this started our long and intensive exchange with Armenia. The contact to Kiev has a similar story, except in the opposite way. So in 1995, I was in the United States, and with a colleague there, we worked out a manuscript for a specific stirrup problem for the scientists. Among those was a 2-photon line width. And then just before submitting it, I realized there is a paper from a group in Kiev, which did treat exactly the same topic, simply in a better way than we did. So we did not submit our paper, and I immediately wrote to Kiev and asked them whether they would like to visit Kaiserslautern. And this was an extremely successful cooperation, and it's still actually ongoing. And then Sofia, there is a little email story, and so somewhere in the spring of 1996, I received an email from somebody which I do not know. The name was Vitanov, and he said, he explained that he's working on stirrup, and he thinks that everyone working on stirrup has before too long visited Kaiserslautern, where this technology originated, this method originated. So of course I was happy about that, and I still remember that we arranged a travel in such a way. I was in the United States, I flew over some morning, arriving some morning. Nikolai came from Helsinki, we met in the lounge of the American Airlines, you remember, and then we traveled back home together, and this really started a win-win situation beyond what I could ever have imagined. So some results 25 years later of these initial initiative and simply being ready to establish these new contacts is excellent science done with the colleagues from Eastern Europe. And just to give you some numbers, we had in the 20 years after this started, in '96 this really started, it was nearly, not quite, but nearly 100 papers which were published from my group, and 80% of those papers were with colleagues from Eastern Europe, and 50% of those were with the group of Nikolai Vitanov. So you see that this really turned out to be absolutely a win situation. And I'm also proud all of them returned to their home countries, and many of them reached leading positions in their countries. And for instance, in Riga, university director and head of laser research center, and in Kiev, director of the Physics Institute, and very important for the science development of the country, he was a founding director of the National Research Foundation of the Ukraine, that is the equivalent to the German Science Foundation, which some of you know. And in Yerevan, he also became director of the institute, and of course in Sofia, we now have a university vice president, and all of them made it to members, full members of the National Academy. So I'm really proud of that, and it's far beyond what I expected. So the initial idea that these exchanges will really have an impact into their home country, to their home countries, really worked out very nicely. So the most fruitful exchange among all of these were actually with Sofia, and this was pioneered by Nikolai Vitanov, and he had experienced science in Western Europe before, and I mentioned, it will become clear why I mentioned this. So during his PhD, he spent some time in Aarhus, then went as a postdoc to London, and then for quite some time, for 5 years, as a young scientist who was also very famous group in Helsinki, and from Helsinki he contacted me, and then he came in '96 to Kaiserslautern, and then for the next 10 or 12 years, every year he was in Kaiserslautern, and 1 year even as a fellow of the Humboldt Foundation, which is a very prestigious fellowship. And then in 2001, he considered to go back to Bulgaria, and I mean, he was well connected already to Western science, and he could have easily achieved a university position in Western Europe. But in the depth of his heart, he wanted to go back to Bulgaria. And we discussed this, and he expressed one concern, and the concern was there was very excellent theory, high energy physics theory done in Sofia. And many of the very good students went to high energy physics for good reasons, and I understand that since it's very important and it was high level physics. So he was worried a little bit whether he would attract good students. And I told him, don't worry. As soon as you show up and establish your group, you will attract some of the very good students to your group. And this also happened. And many of those I had a pleasure also to welcome in Kaiserslautern, and some of them are even sitting in the audience. So Nikolai quickly reintegrated to Bulgarian science and continued and expanded his international network. And okay, this is sort of the history how it came about. Actually, I should also mention that he came back in 2001, and even in 2002, he organized a local conference, since I had organized a European network with some 10 scientists from 8 different countries. And also Nikolai in the beginning was worried, well, locally the infrastructure may not be prepared for that, but I told him, it should be done in Bulgaria, since the example shown by this kind of international collaboration will be helpful, and I think it was really a success. And it was a wonderful meeting that we organized at that time. Okay, now a few words about science, and I was told I should make it in such a way, phrase it in such a way that also some non-physicists could follow. So I now make a few preliminary examples, and at the end, then I hope that you have some impression about what this method syrup, which, as I said, is used worldwide now and taught in classes, in textbooks, and so forth. So I have to make basically two comments. Matter is composed about electrons, which are negatively charged, and nuclei, which have two parts. One is positive and one is the neutrons. And these elements from which all matter is composed, they form atoms, for instance. And here I show the helium atom, where you have two protons, two neutrons, and two electrons. And of course, they are not localized, they are sort of smeared around. And they make an atom. And then atoms form molecules. Again, you have an atom A, you have an atom B, and then there are electrons around, and these electrons provide the chemical bond, so they're chemically bound. And then if you have molecules, from molecules you make liquids or solid materials. And the speciality in my group was small molecules, mostly, but not exclusively, composed of two atoms. So this is what we were working on. And now I talk about these molecules with two atoms, and talk about what kind of energy these particles can have. These particles can rotate, and with rotation there's energy, which is called rotational energy. So they can rotate, and there's rotational energy associated with that. And then, because of the chemical bond also, they can vibrate, and there's vibrational energy associated with it. So we have rotational energy, we have vibrational energy. And they can also have electronic energy. As I already mentioned, the electrons that surround the two atoms, or whatever number of atoms is there, they provide the chemical bond. But these electrons also can increase energy, or you can increase energy, so you have also electronic energy. So we have, for diatomic molecule, we have these three types of energies: rotational, vibrational, and electronic energy. And I will now concentrate for the next few slides on vibrational energy, because this is relevant for why syrup was developed. And in the atomic world, and this is one of the surprising things for those who have not studied physics, the energies are quantized. What does it mean? I try to explain. What does it mean that energy is quantized? I mean, we can have, as I said, I restrict the discussion now to vibration. The molecule can have a small vibration energy, it can have medium vibration energy with some oscillation, or it can have high vibration energy with just much larger amplitude. And if you think of a spring connecting these one with a large amplitude, you need to stress or lengthen the spring more than for small vibration, and therefore there is more energy involved with that. So if you now take an energy scale, you have small, you have medium, and you have high energies. And in the classical world, any energy in between would be possible. But in the quantum world, it's not the case. In the quantum world, these are energies that are possible, and there are a few other energies in between, and no other energies are allowed. So the molecule can change their vibrational state only in certain steps. You have to apply very definite amount of energy in order to go from one level to the other level. So we talk about these quantized energies as the energy levels, and this is a terminology. This is one side of the problem, and the other side is thinking about light. Light is a stream of photons. Right? You don't realize it, but light is a stream of photons. And photons and light is made of electromagnetic waves, and electromagnetic waves have a frequency. So these waves oscillate with a certain frequency. And the elementary particles of light are photons, and they have a certain energy, and the energy depends on the frequency of this oscillation, and there is a constant that every physicist knows. It doesn't really matter here. And you know ultraviolet light, visible light, or infrared light, and the visible light has medium frequency, ultraviolet has a higher frequency, infrared has a lower frequency. So, because the energy of the photon itself, that's the small energy packet that is transported in the stream of light, depends on the frequency. And the frequency that you want to use in order to change the quantum state of a molecule needs to match exactly this energy difference, which is the quantized. So these photons can be absorbed or emitted by molecules, and the absorption and emission, as I already mentioned, will change the energy content of the molecule. So it is through the interaction of photons that we do change the quantum state or the energy of the molecule. And again, at the moment, we can think about only the vibration change. And now we number those. 0 is the lowest one, and then goes up to 8, and could be, depending on the system, could be also go much higher. And now I will show a few slides where you see this blue bar. And the blue bar means that my quantum system is in this particular state. It has this particular energy. You can think of a single quantum state, or you can think of 1,000 molecules. All of them are in this quantum state. It's more or less everything that I'm saying applies to both of these situations. But let's not now mainly think about a single molecule. And usually we have them in the lowest energy state, which we call the ground state. So we can change, I already mentioned it, the vibration state by a photon absorption or emission. That means if we take, for instance, the infrared photon, we can give this energy to the molecule, and it goes from the lowest to the first vibration level. And the probability that this happens, depending on the system, is typically high. It may be 0, but in most cases it's relatively high. You also, if you want to go to a higher energy state, then you need higher frequency photons. The energy packets need to be larger. That means a visible photon, like that. So if you apply a visible photon, you may change the situation, the quantum state, to number 7. And in many cases, the probability that this happens is 0 or very small. This will become important in a few minutes. And in addition to that, I mentioned already we can have electronic energy. So these are the energy levels which I show there in the lowest electronic state. So if I give the electrons also some additional energy, then they are higher on the energy scale. And again, we have these quantized vibrational levels. They may have a slightly different separation, but essentially it's the same situation. So if you want, so the energy scale is expanded to include the electronic energy. And so if you want to excite using visible or ultraviolet photons, so higher energy photons, we can also excite the vibrational energy, increase the vibrational energy in addition to the electronic energy. Okay, so one of the specialities of my group was to control the energy content of molecules through absorption of emission of photons in the way which I sort of explained. The question is, why do we want to do that? Why is this of interest? And there are many, many reasons. I could talk about an hour for reasons, but I only will mention one. Since the chemical reactions between molecules, so if two molecules collide, and what comes out is a different composition of the atoms. So this is a chemical reaction. This may sensitively depend on in which vibrational quantum state, which vibration energy these systems have. For instance, the reaction rate may be very high if the molecule is put into vibration level number 7. It could be very low in level 5. So it was of interest to be able to control the energy of a molecule, 1,000 molecules, all of them in a given vibration state, in order to study the effect of vibration, in particular for the chemical process going up in the higher atmosphere. This was, for some reason, of interest to me, and I wanted to make a contribution. So before we go to zero, I need to go one step back and look at the situation around 1980. So 42 years ago, around. So at that time, we did an experiment that most colleagues who knew about the plan said, this is an experiment that cannot be done. But therefore, I was young at that time, therefore also my philosophy, we have to give young people in science the freedom and have trust in them so that they do things that the old ones think they cannot be done. So we did what is called a cross-molecular beam experiment. Molecular beam is something, atomic beam. You have a vacuum, you have a vessel, you have a high vacuum. So if atoms and molecules travel along, there are no collisions, so they can travel for meters without suffering collisions. So we made a stream of argon atoms or other partners, and then we had another stream of sodium atoms. Again, they would not collide along the way except when they cross the argon beam. So when the sodium beam and the argon beam cross, there could be collisions. And when there are collisions, they would go off in different directions. They would not keep on going straight. So the argon atoms may, for instance, be scattered in this direction, and then the associated molecules that had made the collision would go in this direction. And the interest, for whatever reason, that's not really important at the moment, is the scattering angle. How probable is it that the scattering angle is small, medium, or large? So, and this is called the angular distribution or the differential cross-section. So the intensity distribution of these scattering angle. And in addition, we wanted to know the state-to-state differential scattering. And that means we know prior to the collision in which quantum state the molecule is, and after the collision we also want to know what the quantum state is. And at that time nobody had done such experiments, and with the molecular beam scattering experiments were a big hype in those days. And they had all so-called traditional detectors, mass spectrometer, or whatnot. No lasers were used. And I wanted to change the picture and design a radically different molecular beam machine which relied exclusively on lasers. And the old guy said it will never work. Only lasers, none of these traditional detectors were in there. So only particle of that. And just showing this in a three-dimensional situation again. So we had our argon beam, we had our sodium beam, at the crossing there was scattering, and we wanted to know the scattering, the properties of the scattering, and the blue laser was used to mark the quantum state before the collision, and the green one was used to detect the molecule, the quantum state of the molecule after the collision. And there was a technological new feature that was absolutely important to make what was considered making a scientific dream of the time become true, to really make state-to-state differential cross-section. Few people thought that this could be done. And the technology tool is seen here. What you see here is optical fibers, so there's red light carried along and there's blue light carried along the fibers. And if you now go, nowadays you go to many labs doing atomic physics or spectroscopy or whatnot, you see those fibers all over the place. So this is standard in most places. But this picture is from 1977, where very few people knew about those fibers. Corning had just a few years ago had developed those fibers, and they were not available commercially, and I got them from the research lab of Schott in Mainz, which is the optical company. So most likely, I cannot prove it, but I'm 99.9% sure that this was the very first worldwide, first basic research lab with an optical fiber network. And well, this is 45 years ago. And that means we had a number of lasers, we had a number of experimental stations, and we wanted to, in one day, an experiment where the lasers and the experimental stations are combined in the way I show here. And the next day, we wanted to do a different setup of experiments using different lasers. And you didn't need to realign the lasers in a very complicated way. You simply took the optical fiber and put it from one laser to the other, and then it could be done. This was a matter of basically minutes. So this was a technological tool which we developed. And then the question is, what next? So these were quite successful, these experiments, well, more than 40 years ago. And the question is, what next? And yeah, I give some quotes from my Habilitationsthesis, which I submitted at the end of 1979. And here I will read this to you. Another challenging problem is the preparation of molecules in excited vibration state to study the effect of vibrational motion on inelastic collisions and reactions of relevance to atmospheric chemistry. Since the method that I used to do these experiments, which I just described, relied on the fact that in our molecular beam, these quantum states are already populated. But in a molecular beam, highly vibrational excited states are not populated. So in order to do these studies at the same level of accuracy, we would need it to make them, to prepare them in the state. So this was the motivation. And then nearly complete transfer of population out of a given rotational level, in the rotation level in the lowest ground state to any level in an excited state is desirable. And I also explained in this text that none of the existing techniques would work. So at this time, I did not know how to do it, but I knew this is a problem I wanted to solve. And so the challenge was formulated, and then we started a number of experimental steps, and at the end, we achieved at what is now known as stimulated Raman adiabatic passage, and the abbreviation is STIRA. And as I already mentioned, the preliminary publication was from 1988, and the original, what we consider original publication, was from 1990, and 25 years later, following up on a suggestion of Nikolai, we had a conference in Kaiserslautern on this STIRA technology. Now I'm ready, and I'm coming towards the end, not quite yet, but I'm coming close to the end. And a few comments about STIRA, what it is. This is a task. We already knew, I already explained that we have this quantum structure, and what you see here is a molecule in its lowest vibration energy state, and here a molecule in a high vibration energy state, and we want to make many of those, only in those states. And here is a molecule in an electronic state, which we happen to need, which also has some vibration energy. And the task I defined basically in 44 years ago is to take the population, right? This bar means the population is in this particular quantum state. We want to take all of this population into one state which we decide beforehand. Look at the tables and say we want to populate this quantum state. We want to have all molecules that we deal with in this particular quantum state. And the challenge was to combine efficiency and selectivity. Efficiency means that we wanted to have nearly 100% of the molecules in the lower state put into the upper state, and associated with that is selectivity. We wanted to make sure that this happens, the transfer is to only one quantum state and no other quantum state is populated. And there were reasons for this, why we wanted to have this high selectivity. And as I said, no technique was available, no technique was available that would do that. And so I was essentially setting out for an experiment that, again, many people said, no, this cannot be doable. Go back to your physics textbook and then you will learn it's nonsense, it cannot be done. Well, therefore, give young people responsibility and they will do what you consider impossible. So the immediate situation would be, or the easy solution would be, take a photon of exactly the right energy, so to transfer the molecule from the lowest to the wanted state. But as I already mentioned, in many cases this is not possible. In actually most cases, in many cases, in zero, you cannot do it. So we have to use a detour. So the detour would be to take a higher energy photon, to go to an electronics excited state, and then to encourage the molecule to give up this energy and end up here. So to stimulate it down, this is what we call it, to kick it down and to reach this level. And the question, of course, is, does this work? And the answer is no, it doesn't really work. It looks simple, but it doesn't work this way. And the reason is that I only have shown 3 levels, but in reality there are hundreds of levels, and I show only 4 here. So these are representative for many, many other levels. So as soon as I put the system into the upper state, the electronic state, they will emit their photons in a few nanoseconds actually. They will emit their photons and go to a different energy state, and most of them will reach states, any other state except the one we want to. So that means lots of molecules will make this transition to states where we don't want them, and only few can then be encouraged to go down. So this is a problem, and this seems to be a problem which we cannot solve. But now the puzzling trick, now I'm telling you what the zero trick is, and after you know it, it's very simple. As I said, it's now taught in all atomic physics classes, and the trick is the following. I start offering the system a photon that makes a transition between the immediate and upper state. And this doesn't make sense at all at first glance, because there is no population in these levels, so why should I offer the system a photon or photons which make transitions between levels that have no population? It doesn't make sense, and there is no population. Well, what really happens if we switch on this laser, which is, you see the S laser, and I will repeat that sequence then, and then we start doing tuning it down so the intensity goes to 0, and at the same time the other laser goes up, and see what the population does. So I do it again. So here we start with the S laser, and then we tune it down, the intensity comes down, and the other intensity, the P laser intensity, comes up, and then the population smoothly flows from the initial to the upper state, and there is never ever population in the electronic state, which was a problem because they could decay, and this is not the case here. As I said, it looks weird, and the way how we found that this is another long story, which I of course cannot tell here, but it works, and it's now well understood. That how it happens. Yeah, then we can switch on the laser. And the Thomas group and his students, they pioneered solutions of many follow-up problems, and they also stimulated quite a number of experiments that we did in the past. So there's a famous statement by famous physicists, and I simply show two of them. If you are not puzzled by quantum mechanics, and you should be puzzled about that this works like this, then you haven't understood it. If you are not puzzled, then you haven't understood it. So now the zero concept has now been applied to many other systems and problems. And it's also applied to classical mechanics. And in order to show you again, is in one example, and then I'm now close to the end, one example of how puzzling it is, I show you optical fibers. So what you see here is an optical fiber. They have typically a dimension of a tenth of a millimeter, and then they have a core, which is important for guiding the light. So the core could be a factor of 10 or so smaller. And then you put light in here, and of course, if it's guided, the light comes out there. And the light is not confined only to the core, but it has a distribution. That means if you want to transport light through such an optic fiber, like you have seen it in the pictures, and then there is a certain distribution, and a little bit of light is also outside. So the light flows along the fiber, and if the fiber makes a curve, the light follows, and so this is the typical situation. And now, if we have another fiber, and we put it far away, then of course there is no coupling between fiber 1 and fiber 2, because the intensity of the light from fiber 1 at the position of fiber 2 is very low. So there can be no light going back to fiber 2. But the situation is different if these are close together, because here you see the intensity distribution of the light from fiber 1 is non-zero at the position of fiber 2, so some light can be captured by the fiber 2 and then be transported along fiber 2, and from there, of course, it can be also coupled back into fiber 1. So if you have this situation, light will come out on both fibers. Now let's add a third one. what would you expect here? And the real puzzle comes next. You put in light into the fiber 1, and then there's coupling to fiber 2, and from fiber 2 there's coupling to fiber 3 and back to fiber 1. Because the light field stretches far enough so that the other fibers also see the light and they catch a little bit of light and they carry it along their own core. So you would expect, and this actually is what happens, light comes out of all 3. Now, do a very small change. Simply tilt the middle fiber a little bit. And what happens? We put again light into fiber 1, and question is, comes it out also in all 3? Maybe, maybe not. Well, there is no coupling between fiber 1 and 2 in the beginning. And there is strong coupling between fiber 1 and 2 at the end, because they are close by. And there is weak coupling at the end. So the only rational conclusion would be that all light comes out here, fiber 1 and 2. But it actually comes out all there. And that's good. It's surprising. It's the same, basically the same mechanism as I explained in the atomic physics. Okay, so now really coming to the end. The initial task of Stirrup was to study chemical reactions of relevance to the high atmosphere. That was stimulating the process. But science always often goes in unexpected ways. And nowadays, it's used as a tool worldwide for instance, making ultra-cold molecules, whatever that means. You have a group of molecules, and you put them all into the lowest ground state. And nearly all groups that do it, maybe 90% of the groups that do these kind of experiments, use Stirrup as one essential tool in this process to make molecules in the lowest ground state. And there are many reasons for doing it. Of course, I cannot explain it. Or improving algorithm for quantum communication, and also from the Vitano group, there are a number of suggestions coming along with that. Measuring the electric dipole moment, or the upper limit for the electric dipole moment. Again, I cannot explain here why this is important, but it's of fundamental importance for very basic physical statements about the universe. To know whether an electron, which for a normal physicist is a monopole, has no dipole, but it can have a very small dipole. And there are experiments going on at Harvard. Just a few years ago, they reduced the upper limit for the, so you want to know whether it's 0 or whether it has a finite value. And there are theories that predict it's 0, there are other theories that predict a certain value. So you either measure it, or at least you should put an upper limit. It cannot be larger than this one. And the colleagues from Harvard did an experiment on this, and they reduced the upper limit by a factor of 10, and they are now going, there's ongoing experiment that will reduce it by another factor of 10 and 15, and in both of these, the past experiment and the coming experiment, using Stirrup is responsible for more than 50% of the gain in the sensitivity to push up the limit, upper limit. And as I said, this is of fundamental importance for very basic physics theory. Or, as a last example, to make a single photon on demand. So, typically, when you look at the laser beam, it's a stream of photons that it's a million or billion photons per second, lots of photons. But there are many experiments and so-called single photon sources where you won't have one photon at a time, only one photon, tiny little energy. And they all work in some way like this. You make some kind of trigger, and then a photon comes out. So you make some kind of trigger, and just one single photon, and not more, not million, one. And until the next trigger comes, there is no photon. Trigger and one photon. And among the schemes, Stirrup is also a promising tool to use the Stirrup process to trigger this one single photon. And there are plans to improve, actually, to use Stirrup for acoustic waves. And Chinese colleagues said they are now trying to involve, to work towards improving hearing aids. So Stirrup is for medical things. So I'm really puzzled. But they say it may work. Or there are proposals to store energy in atomic nuclei. That's a proposal. Will this ever work? I don't know. No. So now I'm concluding. There are many more applications of Stirrup realized or in the making. And but the initial motivation to do reactions of atmospheric interest has still not to be done. So if there are young ones around, experimentalists, this is still the ground to be worked on. We did some chemical reactions, but very simple ones and not of atmospheric interest. Right now, of course, I'm associated as a very first slide showed with industry, and I'm working on entirely different things, high accuracy laser ranging, but that is not the topic of today, so therefore I will conclude at this moment. Thank you.
Мирное житие, здоровье же спасение, и во всем благое поспешение.